Isaac Newton, Matter, Math, and Motion. Written by Susan Virgilio. Focus question. Who was Sir Isaac Newton and what did he discover? Connections. Writing and art. Create a poster describing Newton's 3 laws of motion. Include a description of each law, everyday examples, and illustrations that help explain each law. Science. Calculate your weight on Earth, the Moon, and Jupiter. Then write a paragraph explaining where you would weigh the most and the least. Science, great and small. Fruit falling from trees may not capture our interest. Our eyes are usually drawn to grander sights, such as rainbows or sunsets. Isaac Newton, however, was interested in natural events, great and small. His keen observations of everyday happenings led him to ponder the mechanics behind them. His studies and experiments resulted in groundbreaking scientific theories about light, force, and motion that are the foundation of modern-day physics. The Farm Boy Physicist. Isaac Newton was born on Christmas Day, 1642, in the English village of Woolsthorpe, about 100 miles, 161 kilometers north of London. He was the only child of a middle-class British farmer. Sadly, the boy never knew his father, who died 2 months before Isaac was born. When Isaac's mother remarried 2 years later, he was sent off to be raised by his grandmother in the nearby village of Grantham. He did not live with his mother again until she lost her second husband after 9 years. At that time, she sent for Isaac, eager to have her son help manage her property. Isaac was not well suited for the job, however. Although he was happy to be outdoors, he was more of a thinker than a doer. Isaac preferred to spend his time reading beneath an apple tree rather than looking after herds of cattle, and he was soon sent back to his school in Grantham. People who knew young Isaac were impressed with his ability to make working models of machines, such as clocks and windmills. He continued his studies and worked hard to prepare for college. A new school of thought. In 1661, Newton enrolled at Trinity College and started what would be a long association with Cambridge University. Its students followed a traditional course of study that began with the teachings of Aristotle, the ancient Greek philosopher. Aristotle thought Earth was the center of the universe. He described nature in terms of its basic elements, which included some combination of earth, air, fire, and water. Beyond the walls of Cambridge, though, a new way of thinking had taken hold. The scientific revolution that began during the Renaissance was sweeping through Europe. A group of modern philosophers were attempting to explain how the world worked in more scientific and mathematical terms. Thinkers like René Descartes saw the physical world as being made up of tiny particles that were always in motion. Everything that happened in nature was a result of how those particles interacted with one another. Newton learned of this new perspective and became intrigued. Perhaps there was some way to identify these physical interactions and measure them. He had long wondered why objects always fell downward and why light sometimes appeared as different colors. It seemed this new way of thinking might help him find the answers he sought. The Scientific Revolution. Until the 16th century, much scientific thought in Europe was based on ancient Greek philosophy. When new ideas about mathematics and science came to Europe from the Islamic world, it started to change how European scientists investigated the workings of nature. Many people think the revolution began with the Polish astronomer Copernicus, who used math to propose that the sun, rather than the Earth, was the center of the solar system. The exchange of ideas across cultures contributed greatly to the scientific revolution. Instead of doing his course homework, Newton began filling his notebooks with his own notes, which he titled Certain Philosophical Questions. An eager learner, Newton soon mastered what the new thinkers had written. He used what he learned to develop his own theories and calculations. He devised a form of calculus, a type of math used to analyze curves and the areas beneath them. By 1665, the year Newton graduated from Cambridge, he was ready to write a summary of his findings and present them to mathematical scholars in England and other parts of Europe. Fate had different plans, however. That August, an outbreak of the deadly bubonic plague led Cambridge officials to close the university for 2 years. Newton was quarantined in his home with little to do but continue his experiments and write about them. Optics and critics. It was during this time that Newton developed important theories about the nature of light. Descartes had argued that light was a type of motion transmitted through natural substances like air or water. Newton understood that this explained how light moved, but not what it was. In 1666, Newton performed experiments with a prism, which separated white light into bands of color. He wrote that pure white light is a combination of many different colored rays. The individual rays become visible when light passes through glass or water at an angle, a process known as refraction. Newton had discovered how rainbows are made. Newton thought that any time white light passed through a glass lens, some degree of refraction would occur. This would slightly alter the appearance of anything viewed through the lens. In 1668, he used this knowledge to develop the first reflecting telescope, which used mirrors instead of lenses to focus light, thereby forming more accurate images. Meanwhile, Cambridge reopened in 1667. By 1669, Newton was made head of the university's mathematics department. As such, he was required to give a series of lectures on a topic of his choosing. He decided to speak about his recent study of light, explained in his book, Optics. Members of the Royal Society of London heard about Newton's lectures and asked to see a model of his reflecting telescope. The group of scientists was so impressed that they asked him to become a member. In 1672, a delighted Newton presented them with a paper about his work with light and color. One member of the society, however, was not impressed. Robert Hooke was one of the leaders of the Royal Society, and until Newton arrived, was considered the leading expert on optics. He wrote a scathing review of the newcomer's paper and later accused him of stealing ideas from Hooke's earlier work. This enraged Newton and was the start of a lifelong feud between the two men. More critical reviews from other scholars further upset Newton. In 1678, Newton suffered a nervous breakdown and withdrew from public life altogether. Newton's masterpiece. Isolating himself left Newton plenty of time to evaluate and refine his work. He continued to puzzle over how substances and objects interacted with each other. Why did some chemicals react with certain other chemicals? What made water seem to flow up through narrow spaces? What kept the moon and Earth in orbit? Newton thought these mysteries could be explained by some governing principle having to do with force and attraction. Letters from his old rival Hooke sparked a discussion about the elliptical orbit of the planets. The reason orbits were not circular, Hooke said, was because of an imbalance between the forces of attraction and a moving object's velocity. There was a tug-of-war between a moving object's momentum and the pull between it and other nearby objects. Hooke was correct, but his statement was difficult to prove. It was Newton who proved it using calculus. Elliptical orbits. The orbits of both Earth and the Moon are elliptical or oval-shaped. That's because their velocity and the force of gravity are not quite equal. Understanding elliptical orbits enabled Newton to use calculus to more accurately predict and explain planetary and lunar motion. He was able to show their actual movement. This knowledge informed modern moon missions, among other things. Halley's Comet is named for the astronomer who figured out that 3 comets, seen in 1521, 1607, and 1682, were actually one, returning to Earth's vicinity every 75 years. Halley's Comet is projected to return next in 2061. The astronomer Edmund Halley heard about Newton's calculations. Halley visited Newton in 1684 and asked him to send a demonstration of the principles at work. Newton sent Halley a short essay called De Motu, On Motion, which dealt mostly with the movement of planets. Still, Newton thought his explanations did not adequately explain how force and attraction worked in all of nature. Newton continued to work on refining the ideas and calculations in De Motu. 2.5 years later, in 1687, he published his masterpiece, the Principia Mathematical Principles of Natural Philosophy. This landmark book rocked the scientific world and raised Newton's stature internationally. In his book, Newton laid out his 3 laws of motion. His first law states that a body or object at rest stays that way unless a force acts on it. This is why things float in outer space, because no force is at work. In addition, an object that is already in motion will keep moving in the same way unless a force acts on it. For example, if an astronaut were to throw an object, that object would move in a straight line and keep moving in the same direction with the same speed until some force, such as a planet's gravity or a bump from space debris, interfered. Whether an object is at rest or in motion, it has inertia, the tendency to keep doing what it is already doing. Newton also explained that objects are usually acted upon by more than one force, and it's the balance of those forces that determines whether an object will start moving or move in a different way. If those forces are equal, the object does not move or keeps moving in the same way. If the forces are not equal, an object at rest will start moving, and a moving object's speed or direction will change. Newton's second law explains the relationship between mass and motion. Mass refers to the amount of matter in an object. Great force exerted against less massive objects creates more motion or acceleration than against more massive objects. Think about throwing a soccer ball, then a bowling ball. If you throw both with equal force, the soccer ball will go faster and farther because it has less mass than the bowling ball. Newton's third law states that for every action, there is an equal and opposite reaction. We see this law in action all around us. Riding a skateboard is an example. When we push forward with a foot, the wheels move the board forward. The greater our kick, the faster the skateboard moves. The forward motion is the reaction to the backward push of our foot. What you weigh, where you are. Mass and weight are not the same. Mass is the amount of matter in an object. Every object that has mass exerts gravitational pull on every other mass. The size of the pull depends on the masses of the objects. Mass never changes. Weight, however, depends on gravity. The force of attraction between you and Earth is your weight. Since the Moon has less mass than Earth, attraction between you and the Moon would be less if you stood on the Moon, and you would weigh less. Since Jupiter has more mass, the attraction between you and Jupiter would be stronger on Jupiter, so you would weigh more. Do you see the relationship between weight and gravity? Fame and fortune. Although some scientists resisted Newton's ideas, many came to see them as a great achievement. Young mathematicians flocked to Cambridge to learn more. Newton became something of a celebrity. He became friends with Charles Montague, who later became a powerful politician. Over the next few years, Newton's attention drifted away from science and toward politics. In 1696, Montague named Newton Warden of the Mint, and Newton left Cambridge for London in 1701. He was paid well for the assignment, and unlike the previous warden, actively oversaw coin production at the Mint. In 1703, Newton was elected president of the Royal Society. In 1705, he became the first scientist ever to be knighted. Newton spent his later years refining and revising his greatest work, Principia, but did not produce any new papers. He died in 1727, a wealthy and well-known man. Newton not only developed theories, but also used mathematics to demonstrate how those theories worked. His careful note-taking and calculations led a bookish village boy to become one of the greatest and most influential scientists the world has ever known. He forever changed the way we understand the universe. Isaac's apple tree. Did this apple tree inspire Newton's theory of gravity? No one knows, but he did enjoy reading beneath it. Today, the tree still grows at Woolsthorpe Manor, once Newton's family home.
Good job!